Hello everyone, welcome to topic 5.3, concentrations over time. By the end of this, you should be able to identify the rate law expression of a chemical reaction using data that shows how the concentration of reaction species change over time. So we're going to use graphs or be able to plot graphs to determine if a reaction is first, second, or zeroth order. Okay, those are the only ones that are covered in the scope of AP Chemistry. Okay, so starting off, graphing concentration of a reactant versus time allows us to deduce the reaction order as each order produces predictable curves on the graph. By plotting the graph of concentration of a reactant against time, we can see trends and find reaction order. Now, yours may have come out a little blurry, but this says concentration of X when it's zero order is this line. The concentration of Y is first order, so this is first order. And then this one is the second order. Okay. And so we can use these lines to determine if it is first, second, or zero. Okay, because they produce predictable patterns. So we're going to look at those patterns. Notice that for a zero order reaction, the plot of the concentration versus time is linear and it is a negative slope, and that slope is equal to K, or negative K. In the example below, the equation for the line in y equals mx plus b format is given as below. We can rearrange it or write a general expression here. The one on your equation sheet is this. So this is the one you would graph. And this one here is the one on the equation sheet, where the concentration at any point in time is your y, and where time is x. Okay, and then because this is your initial, this is your y-intercept. So this is what it would look like for zero order, but it has to be just the straight concentration. Okay, if we do manipulate the concentration to produce a linear graph, it is a different order. So in the first order reaction, in order to get a linear relationship, you plot the natural log, or ln, natural log is ln, of the concentration against time. This slope is also equal to, so the natural log is equal to negative x. So if you take the natural log of your y and it produces a negative linear line like this one that's shown here, that is first order. So we can write this generic equation using A to represent the reactant species, where this one is the one for the graph and this one is the one that is on the equation sheet. It also has that same format where the concentration at time t is your y and t is your x, where k, negative k is your slope, and k being the rate constant. Okay, so using all of this, and this, how we get to this and figure that out, it's something mathematical, which means it involves calculus. So because the integrated rate law, this is what that is, integrated rate law, because that is given to you on the equation sheet, you do not need to be able to prove that. Thank the heavens. Okay, so moving forward for second order equations or second order reactions, we can plot the inverse of the concentration against time to find a linear relationship. Okay, this slope is equal to the value of k, because k is positive, and we see here that the slope of the line is positive. So in the graph form we have this, and on the equation sheet is written as such, again, where a sub t is your y, and you take the inverse and plot that on your y-axis. So this is your y, and then t is your x. Okay. So when we graph the inverse, this is what it looks like. So if we have a positive slope when we manipulate it, it is going to be second order. If we take the natural log, it's going to have a negative slope and be first order, if we see that pattern. And then zero ordered starts out as linear. Okay, and so we can manipulate the data to figure out if it's first, second, or zero by collecting concentration over time, how it changes. Another way to look at the concentration versus time data is to expect the time taken for half the material to react. So if we look at the half-life, if you compare the blue arrows showing successive half-lives for the reactant, you can see that the half-lives for a zero-order reaction decrease. For first-order reaction, they remain constant, right? That's like nuclear decay. And for second-order reactions, the half-lives increase, so how long it takes for half the reactants to react. There is only one half-life expression on the AP equation sheet, and that is for first-order reactions, where it's written like this. I think it's a lowercase t on the equation sheet, where this is the natural log of 2. If we know the half-life of a material, it tells us about the magnitude of K. The shorter the half-life, the higher the value of K is. So if it reacts very fast, bigger K value. So nuclear decay is an example of a first-order reaction because it has a constant half-life. Every specific number of days or years or specific amount of time, half of your reactants disappear or change into something else. So we have this summary table that is listed here where it is showing you zero, like the concentration versus time, okay, and how do we get the straight line plot. So here you take the natural log, so it stays the same. This one you have to take the ln of your concentrations at time t. And then over here you take the inverse function of your concentrations at time t to figure out what's happening. Okay, and this just keeps continuing the summary. So it's worth mentioning that you can have reaction orders that are fractions. However, it's beyond the scope. And I'm not going to continue to read that because it is beyond the scope. But they do exist, but we won't cover them in chemistry, or this chemistry class. Using the data provided, determine the reaction order and then calculate the value for K with units. Okay, so when we look at this and we focus, we see that we have a curve for the straight, like basic data, your data as is. If we plot the concentration, the natural log, versus time, we have a linear line. And then if we do the inverse, we see it curves again. So when we're trying to figure out which order it is, we're going to look for the one that is linear. So we're going to look for linear. And we see that the ln function is linear. So that tells us that the reaction order for this is first order. And this is just something you have to remember. And so now we want to figure out K. So for this, we see that for this one, that K is equal to the negative slope. Right? So this here is our slope. And so I'm going to write it up here. K is equal to the negative of negative 3.15 times 10 to the negative third. Okay. And that tells us that it is positive 3.15 times 10 to the negative third. And then we have to figure out the units. Well, you can either remember what the units are for each. For K, so first order is inverse seconds. S to the negative 1. And so if you remember the units for first, 0, and second order, as they are shown here, then you know what the units are for K. Okay, and so it just simplifies where it's molarity per second, and you just get rid of a molarity each time. So this is 0 per second, or inverse seconds is first, and then per molarity seconds or molarity seconds is second. Okay. You could also calculate it, because the rate law would be is K times the concentration of our reactant, which is here. This is our reactant, and we know it's first order, so it's to the first power. So the rate is in molarity per minute. Oop, this should not be seconds then, this should be minutes. M-I-N. Molarity per minute is equal to K times molarity, and if we're going to solve for the units for K, it'd be per minute, or inverse minutes, as shown here, because the molarities cancel out. Okay. Looking at the WEDO, the decomposition of blue dye using bleach was studied. The concentration of bleach was 1.3 molarity, while the concentration of blue dye was 6.2 times 10 to the negative 6 molar. The reaction was monitored by measuring the absorbance at 630 nanometers. Ooh, that's Beer's law. Since the concentration of bleach is many times higher than the concentration of blue dye, we can assume that the concentration of bleach remains constant throughout the reaction. It's so large that it's not changing significantly compared to the initial amount. So you can ignore it and just say, hey, it's there, but it's going to react, so this should actually be an arrow right below it. I think the arrow part got cut off. Okay. Based on the information provided, what is the reaction order? Explain. So for this one, you could graph it, and if you have a graphing calculator, this is where they come in big handy. However, we also know that half-life plays a part in the types, and you're only going to be asked for 0, first, or second. So you have to determine which one it is. So if I look at the half-life, so my amount when it halves here, okay, so that is a half-life of 30 seconds. Then I'm going to look at 0.44 halved again, which is here. So there's another half. And then I'm going to check, how does the half-life change, or does it? And I see that here it is 30 seconds, and then 30 to 60 is another 30 seconds. So since my half-life is constant, my reaction order is first order. Because first order reactions, if we look back in our notes, somewhere up here, this one, a constant first half-life is first order. So we would say the half-life is constant. So the order, the reaction is first order, sorry. And that's all she wrote. So thank you guys for tuning in. Work on the UDOs, check your work as you go, and thank you for watching.